all and welcome to this lecture. We are in module 10, lecture number 3, the quest of ever small devices. In this lecture, we will discuss about classical scaling, modern scaling and emergence of novel devices. These are the learning outcomes of this lecture, which helps you to understand what is the meaning of device scaling, what are the classification of classical scaling like constant field scaling, constant volt scaling and some generalized scaling. We will see why the need of modern scaling is important and what are the emergence of novel non-planar devices. Let us do a quick recap. In previous lecture, we have said that when the device dimension shrinks, so the electric field near the drain channel junction will be very high, and hence because of this heavily doped drain channel junction, there is a possibility of quantum tunneling or band to band tunneling. So, if this is p plus in n junction which is heavily doped, then there will be a possibility that the electrons will tunnel from the valence band of the p side to the conduction band of the n side. This gives rise to a current which is nothing but a leakage current. This phenomena is important when you are talking about small channel devices and heavily doped p plus n junctions. We have also discussed about jiddle, when the drain overlaps, when the gate overlaps the drain. We said that this is also cause a leakage current. In the later part, we discussed about the possible leakage current or leakage path in different application like digital on operation, digital off operation and analog operation. So, we have discussed about the short channel effects thoroughly. Now, how we can go from a long channel device to a short channel device? Definitely there would be some prescribed rule. So, the semiconductor industry growth is depend upon this rules or some set of rules which helps to design or to find the new technology generation, which leads the high speed circuits and low power circuits with low cost per function. The continuous reduction in device sizes commonly referred to as scaling. Until around year 2000, the device scaling adhered with some set of rules. With some prescribed rules, we were scaling from the long channel device to short channel devices. That is what it is called classical scaling. However, post 2000 or post 2005, we cannot follow the same rule to find out the new technology. That is what comes under modern scaling. Let us take an example that I do have an NMOS where this is source, this is drain and body and gate. The channel length is defined between source and drain. Now, from the long channel device, I want to design a short channel device considering all the electrostatic holds good, meaning the depletion region charge will be same as this. Then what I will do, I will follow some set of rules that comes under Dennard scaling. It means I will scale all the dimension by a factor of k, right. For example, if the length here is L, I will decide or design a new length of new technological MOSFET with L by k. So, there are two types of classical scaling. One is constant field scaling and one is constant voltage scaling. Constant field scaling means while doing the scaling from long channel to short channel, the field, the electric field in the device will be constant. It is not getting changed. And what is electric field? Electric field is nothing but V by L, meaning if the L is scaled by k, the voltage is scaled by k, or in other way around you can say if the voltage is scaled in new technology, then the dimensions will be scaled by the same factor such the electric field will be constant. Maintaining the constant electric field prevents the reliability issues such as oxide breakdown, velocity saturation, etc. The other way of classical scaling is constant voltage scaling. where we will scale the dimensions keeping the voltage constant. So, we will see one by one. Let us consider first the constant field scaling. As I said that if I am going to design a short channel device considering the field is constant, then if the voltage which is applied between terminals is scaled by k, then the dimensions will also scaled by k, right. So, if V is scaled by k or V by k now, then L, W, Tox, junction depth, all the dimensions should be scaled by k. So, I am sorry, this will be L by k, W by k, dj by k, similarly Tox by k, etc. Now, considering that depletion charge or depletion depth will be same, right. So, the depletion depth should also be scaled by k, maintaining the depletion charge will be same. So, if the depletion depth is scaled by k and voltage is scaled by k, then what about doping concentration? You can simply see d by k is equals to square root of 2 into epsilon divided by q into Na into some phi b I plus V divided by k, which means the Na is increased by k. So, I can simply say the voltage and the dimensions are scaled by 1 by k and the doping concentration is scaled by k. Likewise, we can find out what are the other parameters when you are going from long channel to short channel. For example, gate capacitance per unit area COX dash, which is nothing but epsilon divided by TOX. As we said that in constant field scaling, TOX will be scaled by 1 by k. So, epsilon divided by TOX by k. So, the oxide capacitance per unit area will be scaled by k. It will increase when you are going from long channel to short channel. However, the overall capacitance, which is nothing but COX is equals to W into L into COX dash, will be W is scaled by 1 by k, L is scaled by 1 by k, whereas capacitance per unit area will be scaled by k. So, the overall capacitance will be scaled by 1 by k, and hence the overall capacitance will reduce. Similarly, we can find out the charge per unit area. So, if you see the charge per unit area, as we have seen that C dash or capacitance per unit area is scaled by k, whereas the voltage is scaled by 1 by k. So, the charge per unit area is not scaled, right, whereas the total charge will be scaled by 1 by k square. Similarly, you are putting all those definitions and find out how the current, the delay, the subthreshold slope are scaled by either 1 by k or it will increase by a factor of k. So, if you see the current equation of MOSFET, then IDS is nothing but mu W. W will be scaled by k when you go for shorter or small channel devices. L will be scaled by k. COX dash will be multiplied with k. VGS minus VT. So, all voltage will be scaled by k. So, ultimately you will get what? VGS minus VT whole square divided by k square. So, this ultimately you will get the current is scaled by 1 by k in short channel devices, right. Similarly, the delay will also reduce, right. So, delay you can calculate q by IDS. By doing so, you see that when you are going for short channel devices, it is more feasible for high operation or high frequency applications, correct. So, this kind of scaling comes under Dennard scaling, which is the foundation for classical MOS scaling. These are some parameters listed out which shows that how these parameters will be scaled when you go from long channel to short channel devices. Like we have mentioned that the device dimension will be scaled by 1 by k, the area will be 1 by k square. Similarly, packing density k square times, that is what the meaning, right. You have a complete, you have long channel devices, and when you are shrinking down devices, the packing density will be increased. Similarly, the bias voltages, bias current, you will get all these multipliers, either it is 1 by k, 1 by k square or so. Let us take another example of body effect. So, body effect is defined as what? Square root of 2 into q into Na into epsilon s divided by Cox dash. We have seen that Na will be scaled by what? K. So, new body effect for short channel device is can be given by 2 into q into Na into epsilon s into k, right, divided by Cox dash is scaled by k. So, ultimately the body effect is going to be scaled by 1 over square root of k. Let us see some important parameters as subthreshold slope. We know the subthreshold slope is defined as the slope of I, ds and Vgs when plotted in log scale, right, and this slope is can be given by n is equals to 1 plus Cb dash by Cox dash, where Cb dash is a bulk capacitance and Cox dash is oxide capacitance per unit area. As we have seen that the oxide capacitance per unit area is not scaled, meaning n will not be scaled, right. So, when you are going from long channel to short channel devices, your subthreshold slope is not scaled. So, this is not desirable for digital application because it will reduce your noise margin. Similarly, let us consider about the contact windows, meaning you have n plus source and drain and you make some contacts like this, right. This contact this contact is made with some area, right, and the area is scaled by 1 by k square. Now, the resistance of that contact will be scaled by k square, correct. So, if the current is scaled by 1 by k, then what about voltage? V is equals to I into R, this is 1 by k into k square. So, the voltage will be k times. It means the voltage drop near the contacts will be scaled by k, which is undesirable again, right. There is another definition of electromigration. What it means is, suppose you have a MOSFET and in the MOSFET the metal or the polysilicon is used to define the gate. So, let us consider the W is the width of the poly or metal line and H is the height of the metal or poly line. If I am going for scaling, then this W will be W by k, H will be H by k. So, the overall area of this metal or poly line will be what? 1 by k square, and I know that the current flowing through this will be scaled by 1 by k. So, what is the current density? Current density is nothing but I by A, I is scaled by 1 by k, area is scaled by 1 by k square. So, the current density will be scaled by k. So, the current density in short channel device when you are scaling with k ultimately increase, and hence it carries the atoms along with it. This actually causes a line failure. This is called electromigration. So, scaling is not coming with free of cost, we need to pay multiple things, right, and we need to optimize accordingly. Now, what are the limitation of classical scaling? As we have said that if we follow a constant field scaling, meaning what? As we have said that we are following the constant field scaling, meaning what? If the voltage is scaled by 1 by k, then the thickness is also scaled by 1 by k, right. So, if this is a MOSFET and this is an oxide thickness which is TOX, then from one technology to the newer technology if I am going, then if I am scaling the voltage by 1 by k, then the oxide will also scale by 1 by k, meaning the classical scaling theory says I can scale the TOX to a very small value, which is not the case, because when you scale the TOX to a very thinner value, then what will happen? There will be a second order effect comes into picture, like gate leakage, what we have discussed in our previous lecture. Similarly, when you scale the dimensions, for example, the channel length from longer channel to shorter channel you scale like this, then there will be a dibble comes into picture, threshold voltage roll off because of dibble, comes into picture, charge sharing will come into picture, and hence you cannot simply follow the prescribed rule of Dennard scaling to find out the newer technology. That is what we need to do some optimization in classical scaling. The one way out is use the quasi constant voltage scaling or quasi scaling, meaning it is not mandatory that all the parameters like voltage and dimensions will be scaled by a same factor. You can choose the factor like k dash. So, if I am scaling, let us consider the dimension by 1 by k, then the voltage will be maybe scaled by 1 by k dash, where k dash is less than k and greater than 1. Or I may use the constant voltage scaling, right, based on the application and based on the definition of newer technology where I am planning to move, correct. However, this classical theory or classical scaling theory is limited till 2000, but post 2000 what happened, the classical theory violates some rules. Now, we will discuss about modern scaling. As I mentioned that until around year 2000, the MOSFET scaling followed the well defined rules. However, post 2000 these rules are not valid, meaning you have to think about some modern scaling technologies, some modern scaling rules or techniques to find out the newer technologies. Broadly speaking, the CMOS logic family is classified as high performance CMOS, low operation power CMOS and standby power CMOS. So, the application of these logic families are like, for high performance we are using in servers, workstations, etc. For low operation power we are using in notebook computers, etc. and low standby power like we are using in portable handheld devices like cell phones. So, accordingly we need to scale, and according to the application we need to find out new modern scaling technique to find out the newer technology. As I mentioned, when you go for scaling from the longer channel to shorter channel, then multiple short channel effects come into picture. For example, high source drain doping causes leakage, that is what we have already discussed. Subthreshold degrades, just we have seen that the n is not scaled, right, in classical theory definition. If subthreshold is not scaled, then you need to think about some other way around to scale the subthreshold slope. Similarly, when you go for a shorter devices, the electric field will increase, which causes hot carrier effect. The shrinkage of the device dimensions like width causes charge sharing effect. Similarly, it causes dibble, CLM, etc. So, we need to plan for some non-planar devices, right, or some modern techniques with which we can scale our basic planar MOSFETs. This picture will give you a complete idea how the scaling proceeds. Broadly, the scaling is divided in 4 subcategories. One is geometric scaling, equivalent scaling, channel structure scaling or 3D integration. Before 2003 or around 2000, we were actually talking about planar MOSFETs, right. Like what we have discussed in this course, we have source, drain and the gate at the top. So, the gate is controlling the channel charge from one end. After 2003, what happens, as the classical theory of scaling violates the rule, in the sense, as I said that if I want to scale to a newer dimension, let us say from 180 nanometer to 90 nanometer node, right, where these 180 nanometer, 90 nanometers are the channel length, whereas strictly speaking these 7 nanometer, 5 nanometer, 3 nanometer, 2 nanometer are not the channel length, right. So, in earlier technology these nodes are related with the channel length. So, if I want to scale the channel length from 180 nanometer to 90 nanometer, then I need to scale the voltage accordingly and the oxide thickness accordingly. So, what happens is, when you scale this geometric scaling, then what happens, the oxide thickness is very thin. So, researchers suggest that why not we will use some high K dielectric to avoid that gate leakage. You remember we have discussed about effective oxide thickness, where I discussed that instead of using simple silicon dioxide layer, we have a stacked oxide layer. So, this is silicon dioxide and over which you stack with a high K dielectric, such that the effective oxide thickness over the MOSFET will increase. So, this is the era when we were discussing about some advancement in planar MOSFET, like strained silicon, like silicon germanium, like EOT, high K dielectric. In 2011, after introduction of FinFET, the things got changed from equivalent scaling to structural scaling. It means from planar MOSFET we entered into non-planar structures. Now, what is FinFET? You have a gate like this, which actually wrapped the channel from 3 sides, right. So, this is what you have: source, drain, and in between this region is your channel over which the gate is wrapped from 3 sides. So, wrapping the gate from 3 sides will give you more gate electrostat and hence reduction in short channel effects. Now, post 2023, the research entered into non-planar GAA, which is gate all around FET or gate all around transistor, under which we mention about nano sheet FET, fork sheet, and complementary FETs, right. There are also nano ribbons, nano wires, etc. What it means is you have source, you have drain, in between you have a channel like this, and you wrap the channel from all the 4 sides. That is what it is called gate all around structure. So, in the expected trend of scaling will go after 2 nanometer, it will go in angstrom, and in that angstrom we need to reduce the footprint area. Instead of having horizontal stacking, we will go for vertical transistors, right. So, these are the scaling theory from year 2000 to expected in 2032 or so. In this graph, this shows the transistor density. As you can see, in earlier days the transistor density per centimeter square is around 50 million, whereas now we exceeded to 300 billions. This also shows the evolution of lithography techniques, right, from 2003 to expected in 2032. So, we can say that the scaling trend or the modern scaling trend gave us the non-planar structure. The planar MOSFETs converted into non-planar structure in structural scaling. During this year, many solutions has been suggested, like I mentioned the strained silicon, silicon germanium, right, in these technology node. But post 2011, what happened? The tri-gate FinFET came into picture and we entered from planar MOSFET to non-planar MOSFET. These are some of the issues and solutions mentioned for different node of the devices in different era, which says that when you are going for GAA, we are actually cutting short of power, area, and cost, right. Likewise, this complete modern scaling will give you emergence of novel devices. So, I am not going to discuss in detail, but let me introduce some of the novel devices which is actually govern the semiconductor industry nowadays. This is the bulk MOSFET, what we have discussed so far, right, where this is source, drain, gate, and this is substrate or body. The control of the channel, the control of the gate over the channel charge is only from one side, and there are another problem of leakage, what we have discussed in previous lecture. To avoid that problem, we entered into what? SOI structures or fully depleted silicon on insulator wafer. So, instead of having bulk, we have a oxide layer, and over which extreme thin silicon layer is grown, as this is drain, this is channel, this is source, and over which this is oxide, and you mounted the gate, but still the control is from one side. If you reduce the oxide thickness, you can control from the other side, that is what? Double gate structure. But in 2011, the introduction of FinFET changed the complete technological growth of MOSFET, and we entered into non-planar structure. What it says is, you have source this side, it is like a 3D structure, you have a source this side, you have a drain this side, and in between you have a channel, and the channel is like a fin. So, this is your channel, and now channel is wrapped from all the 3 sides like this. So, this is your channel, and ultimately what you are doing, you are wrapping from 1, 2 and 3 side. So, this is the FinFET. Between source and drain you have a channel which is wrapped from the 3 side. This is FinFET. Now, what happens is, to reduce the footprint area, instead of having horizontal stacking, right, what we will do, we will go for vertical stacking. Like this is one channel, this is another channel, this is another channel, like that, and each channel is wrapped from all the 4 sides. That is what is called nanosheet FET. So, you have one channel between, this is source end, this is drain end, and you have a plate like this or the channel like this. Okay. And now, what you are doing, you are wrapping this channel from all the 4 sides. This is your gate, correct. So, ultimately the gate electrostatic is increased, whereas you can reduce the dimension also. So, it will reduce the node, that is what it is visible here, that you are entering towards the 2 nanometer or 3 nanometer node technology. Now, with this evolution also there is a problem in the sense of problem in terms of NP spacing, meaning in the circuit whatever you are going to design, for example, the logic application, then you require both the transistors like NMOS and PMOS. So, you have to maintain a minimum spacing between NMOS and PMOS. For example, if I take a CMOS inverter, generally we design the CMOS inverter as connecting a PMOS here and NMOS here, and we shorted the gate, apply the input here and take the output from the drain. In this basic logic application of CMOS inverter, we require both the transistor, that is N and P, N and P. So, now suppose I want to design a CMOS inverter using FinFETs or nanosheet, then I need to maintain a sufficient spacing between these transistors. So, the possible solution to again reduce the footprint area is go for forksheet or CFET. What it means is, in a single device you have N type MOSFET and P type MOSFET, which is separated by a dielectric wall, right. So, this is the structure of forksheet FET. Again, to reduce the footprint area, right, what it suggested as, instead of having again horizontal stacking, why not you keep the NFET or the nanosheet sheets of NFET to the bottom side and the sheets of PSHAT to the upside. That is what this is, PFET here and NFET here. You can stack vice versa also. For example, if you see this structure, this is nothing but CFET. You have a substrate over which you grow first the NFET or PFET, and then you have a dielectric wall, and this is PFET. So, a single device is nothing but acting as an inverter with proper appropriate voltages. If you have 5 terminal, basically drain, source, this drain, this source and the gate. So, if you have a 5 terminal, you will connect the appropriate voltages, then a single device act as an inverter. No need to connect externally these two NFETs and PFETs, right. So, this defines the emergence of novel devices, where the physics and the theory what we have defined for for bulk MOSFETs is simply applicable with proper optimization and modulation. So, let me summarize that in this lecture we have discussed about the scaling, which is an important fundamental approach to grow the semiconductor industry. We have said that earlier 2000 or around 2000, the MOSFET follows a well defined scaling rule, which comes under classical scaling. The classical scaling is defined as constant field scaling and constant voltage scaling. In constant field scaling, we are maintaining the field, the electric field will be constant, which is nothing but VDS divided by L, or in general V divided by L. So, we need to scale the voltage and the dimension accordingly. Constant field scaling is good in terms of reliability aspects, whereas we have also said that when the classical scaling fails, then you can go for some quasi classical scaling, meaning you have to take some parameter of scaling k dash in between k and 1. Then post 2011, when the FinFET was introduced, we entered from planar MOSFET to non-planar technology, and hence we were moving in reduction of the dimensions from 22 nanometer or 32 nanometer to 1 angstrom, right. That is what comes under modern scaling. Modern scaling is not following a prescribed rule, but yes, we are maintaining the integrity of the planar MOSFET to hold good. The physics and the mathematical modeling of planar MOSFET, what we have discussed so far, is simply applicable in non-planar devices with proper optimization and modulations. So, we will stop here for today. Until then, take care.